Hello again. In this video we're going to start with this important theorem that says a square matrix A is invertible if and only if the determinant does not equal 0. You can show this by what we did in the last video. So if you let A be an n by n matrix by the invertible matrix theorem, we know that A is invertible if and only if the columns of A are linearly independent and there are n pivots. And what we did last time is we reduced A to find the determinant to echelon form, and the determinant, using the fact that the determinant of a triangular matrix is the product of the diagonal of the entries, we know that the determinant is not equal 0, since that there are n, for the n by n matrix, pivots that are non-zero. So when you reduce it to echelon form, you get that triangular form. All those pivots are numbers, they're not 0. If there was a 0, there wouldn't be n of them. And you have it. Note, we can go the other way around as well. When the determinant is 0, it's not invertible. The columns of A are linearly, oops, made a mistake, dependent. Which is great. It's another way to show if the columns of A are dependent. You can see if the determinant is 0 or not. If it's 0, we know it's linearly dependent. Otherwise, it would be independent. So you can see here in example 3, just let's glance at example 3 here. It says compute the determinant where A is the following matrix. And all they did is they realized that if you take 2 times the first row and add it to the third row, and put it back into the third row, you're going to get the same line, so that when we subtract those and do the echelon form between those two, get the pivot now here and get a 0 here, you're going to get a row of zeros. So without doing anything else, you can determine that the determinant is 0. Another useful fact is that if A is an n by n matrix, then the determinant of the transpose is the determinant. It does not change the value. You can check out the proof in the book. I will not do it here, but they use induction. A lot of these proofs in this section, because it's an n by n matrix, are done by induction. But let's look at an example of this. Let's just start with a 2 by 2. We know that the determinant of A is AD minus BC. And then if we take the transpose, that would be AB. The rows become the columns, and the columns become the rows. You can see that the determinant of the A transpose does not change anything. Use the same notation there. So therefore, the determinant of A transpose is the determinant of A. And this works for any size matrix. For example, let's do this example. The determinant of A, I'm going to use maybe the third column, plus, minus, so that would be a 1. And multiplied by the determinant when I cancel out the second row, third column. So you get 1, 5, 0, negative 2. So the answer to this we can see is negative 2. If you look at the transpose, it should not matter, because we can use any row or any column, so I'll just use that same one. and you would get the same answer, plus minus plus minus. It is the same value. It's a 1, and this would just be the transpose of this. When we cancel that third row, second column, we get 1, 5, 0, negative 2 actually. So the answer is still negative 2. Here's the actual proof if you want to read it. Again, they use induction. They show it's true for 1. And then they assume it's true for k, a k by k determinant. And then they talk about the cofactor expansion of A1j. NA equals the cofactor expansion in the transpose. Because of the rows, you could use rows or columns from the last video. Hence, the cofactor expansion of the determinant A along the first row equals the cofactor expansion along the transpose down the first column. So they have equal determinants. It's true for n. The truth of the theorem for one value of n implies the truth of the value for the next value. So if you've ever heard of induction, that by the principle mathematical induction, the theorem is true for all n. So induction says if it's true for n, assume it's true for n. If it's true for n plus 1, then it must be true for all n. The following theorem we're going to use a lot in our next section, which is if both A and B are n by n matrices, then the determinant of A times B is the determinant of A times the determinant of B. This is very powerful. The proof of this one is in the book at the end of the section. If you want to read about it, we won't prove this one, but it is in the book for you to look at if you're interested. But let's verify it. So what they did here is they took A times B and they multiply them together. So you can see you get 24 plus 1 is 25. To get the 20, you take the first row, second column, you get 18 plus 2 is 20. To get the 14, you take the second row, first column, so you get 12 plus 2. And then finally, the second row, second column, we did this in the last chapter, 9 plus 4 is 13. You look at the determinant, we'd multiply these and subtract these, you get 45. If you just look at the determinant of A, that would be 12 minus 3, which is 9, and then 8 minus 3, which is 5. It's also 45. There's a warning. A common misconception of Theorem 6 is that the determinant of A plus B is equal to the determinant of A plus the determinant of B, which is not true. They're not equal. So it only works for multiplication. The proof of the general theorem does use induction and the idea of elementary matrices that you can look at. But I'm just going to show it for a 2 by 2. So let's let A equal A, B, C, D. And let's let B equal E, F, G, H. Let's just go ahead and find the determinant of A. We know is AD. Well, let's just write it all together. Times the determinant of B. Let's just do the right-hand side first because that's just AD minus BC times EH minus FG. Okay, so that's what we want to get when we take the determinant of A times B. So what is the determinant of A times B? So we have to multiply them first. So let's go ahead and do that. When you multiply A times B, this would be the first row with the first column, so you get AE plus BG. First row, second column, AF plus BH. Second row, first column, so CE plus DG. And then second row plus second times second column would be CF plus DH. And if we just find the determinant of that, So you get this times this minus this times this, and you think this is a mess, but it actually works out nice. So if you FOIL this out, you get the first 4 terms, and then if you FOIL this out, you get the next 4 terms all with minuses, because there's a minus in front of there, and then things cancel. So we're only left with 4 terms, and I'm going to reorder them so the ADs are together. So that's those two. And then I have BCGF left with a minus BCEH, and I just factor by grouping, and it's going to all work out. AD is common. I actually want a minus. I want these to be the same, so I want this to be first. So I'm going to actually take out a minus BC and then put this first, so it looks like this, minus FG. And then we have it, AD minus BC. What's common is this. Actually, I should have done that first, but that's okay. That is, if we make this smaller, whoops, what we got here to start with. And that concludes this section.